Okay, we'll get started. So welcome to this Physics Paper 2 class, the last class for this GCSE series. So just like all the other classes, I'll run through some exam questions. We'll go over content in the next hour as well. If you've got any questions, there's a chat open on the side, so you can just type in messages as I'm going along the class. The class is also being recorded as well, so it'll get uploaded as well after, so you can refer back to this class as well. So let's just get started. So for physics paper 2, you're going to be using the second half of the equation sheet. Yeah, I'll definitely say when I'm doing higher. Higher is just going to be towards the end, Liber. So the first part is foundation and higher. Just towards the end, it'll be higher, so you can drop off after that point. Okay, so this is the second half of the equation sheet you'll be using for tomorrow. Just like the first exam, you need to memorize all the units for each of these. And you should be familiar with how to rearrange all of these as well to use them to your advantage. So, for example, you should know that weight is a force, and force is always in newtons. Also, when you're using the equations as well in your calculations, make sure you actually write down as well which equation you're using, because you get a method mark for that as well. So weight is a force that's in newtons, mass is always in kilograms, and so on. You should also, from the equations as well, figure out how certain factors affect the equation. So for example, with the weight, if I decrease the gravitational field strength, so on Earth, it is 9.8. On the moon, it's less. I think it's 1.8, but you don't need to memorize these. They will give you these in the exam. But as you can see, on the moon, the gravitational field strength is less. So because we're decreasing the gravitational field strength, that's going to in turn decrease the weight. So you weigh less, you have less of a weight, which is a force, on the moon compared to the Earth. Likewise with other things as well. For example, acceleration. If I increase the time on the bottom, for example, it takes for, I don't know, a car moving, then that means acceleration will decrease. So because it's a dividing thing, so if I increase the denominator, this will decrease the overall acceleration. So you can figure out all these factors being affected just by using your equation sheet, so you don't need to memorize them. Example, resultant force. So this is Newton's second law you should be aware of. If you increase acceleration, that's going to increase the force, just like with if you increase the mass, so something heavier will have a higher force compared to something that weighs less, which has the same acceleration. So you can figure out all these just by looking at the equation, so definitely use it to your advantage. So I've got a table here with some units you need to memorize. If they give you mass in grams, make sure you change it to kilograms. So how do you go from grams to kilograms? Well, remember, in 1 kg, you've got 1,000 grams. So any time you see the word kilo, it means 1,000. So even kilometers, it's 1,000 meters in 1 kilometer. So to go from grams to kilograms, we're just dividing by 1,000. Time is always in seconds. So if you get given something in minutes, change it to seconds. In 1 minute, you've got 60 seconds. Length is always in meters. It's quite common that they give it in kilometers. Make sure you change it back to meters. Another thing people forget as well, length is also the unit for wavelength. So remember, wavelength is the, so let's say I had a wave. Wavelength is the completion of one full wave. So it starts on top and it goes towards the bottom. So I should have drawn that a little bit better. So it's one complete wave is what wavelength is, and that's in meters. Wave speed is in meters per second. Frequency is in hertz. Okay, cool. Meters per second for speed. Energy and work is always in joules. Frequency in hertz. Power in watts, which they don't really assess you on this exam. That's more paper 1, but they can. Temperature, degrees Celsius. These ones, really, they're paper 1, to be fair. These ones are paper 1, so you don't really need to know these ones, but just be aware of them. So that's paper 1. Forces in newtons. Remember, weight is a force, and acceleration in meters per second squared. If you do forget the acceleration unit, again, you can figure it out from the equation here. So acceleration is change in velocity. Velocity is meters per second divided by time taken, which is seconds. If I'm dividing by another second, I can say meters per second squared. So you can use a bit of basic maths as well to figure out units as well, just in case you forget. One other thing I want to mention as well about this equation here. So final velocity is always your velocity at the end. Initial velocity is your starting velocity. Now, sometimes in a question, they won't give you the actual number for these, they'll just use words. Now, if the question says it's starting at rest, what this means is the initial velocity will equal 0. So the initial velocity will equal 0 if you're starting at rest. If you come to a stop, so I don't know, a car's driving and then it stops at the end, that means the final velocity will equal 0. So just be aware of these two terms. You're coming to a stop or you're starting at rest. It means like you will either put your initial velocity or final velocity at 0. So they won't explicitly tell you in the question that is 0. Another thing as well with all your calculation questions, if it's 2 marks, 3 marks, you'll just be using one equation. If it does end up being a 5 marker or 6 marker question, you're using 2 equations. So you just need to figure out what you've been given and then find out what to find out from they've asked for, essentially. Sometimes this is actually an interesting one as well. So sometimes they might ask you to find force of a certain thing in a question, but they've only given you, so if they've said find force of something, the resultant force of something, but they've only given you the mass and they've given you the gravitational field strength. Usually when you're finding force, the one that you think about is mass times acceleration, which is over here. So this is the one that you think about when you're trying to find force, but we don't have acceleration given to us in the question. We've got mass and gravitational field strength. So another one that involves both mass and gravitational field strength is this one here. So you need to remember that even though the question has asked you to find force, force is exactly the same thing as weight. Weight is a force. It's a vector. It's in newtons. It is a force. So really in that question, they were asking you to find weight, but they didn't use the word weight in the question. They used the word force. So just keep that in mind as well. Okay, sometimes they could ask you, well, we'll go through some exam questions and then we'll come on to that. Okay, so starting with contact and non-contact forces. Contact forces occur between two objects that are physically touching each other. So for example, friction, if I was rubbing my hands together, there's heat getting generated, it's a frictional force. Both my hands are touching each other, it's a contact force. And non-contact forces are where the objects are physically separated. So going back to chemistry, imagine with ionic bonding, you've got a positive ion touching a negative ion. So they are attracted to each other. There's a force, and that force is called an electrostatic force. But because it's atoms and it's essentially the fact that it's a positive charge and a negative charge, we call this a non-contact force. So just keep that in mind. So this question here says, magnetic force is a non-contact force. So magnetic force as in between like a north pole and a south pole, they attract, opposites attract. Which two of these are also non-contact forces? So air resistance is a contact force because it acts, say there's somebody jumping out of a plane, the parachute would allow for air resistance to be created. So it's a contact force touching the parachute and it's on the person as well. Electrostatic is a non-contact force, as we've just discussed. Friction is not, because you're rubbing your hands together, it's not. Gravitational is also a non-contact force because gravity is not essentially touching anything. It's there. It's a force that's down. Okay, so they're your non-contact forces. Keep that in mind. How to draw a magnetic field. Now remember, magnetic fields, you always draw it from north to south. It's a bit like with paper one, electricity. You go from the north part of the battery to the positive part of the battery, sorry, to the negative. With magnets, you go from north to south. And the way you draw them, let me put this over here. You draw them like so. So you will see magnetic fields. It's a bit like this around the Earth as well, but they can't really draw circles out that big. So the way you usually see them, actually, let me put the arrow on first as well. So it's north to south. So it's going from the north to the south. So the arrow would be like so. So going from north, these are on the north ones, by the way, to the south. So again, north, sorry, I should have actually made these a bit more explicit. Let me just draw that again. My line should have really explicitly been on either the north and south and not ambiguous, just floating in the middle. So let's start over here. So that's north to south. So just like so. But in the way you see it is sometimes you see them drawn like this. Like it'll just be coming outwards like this. So I'm gonna show you a picture rather than drawing it. I'll show you on the Earth actually. So remember, we've got a magnetic field on the Earth because we've got a North Pole and a South Pole. So a magnetic field on the Earth. Hopefully it's a nice picture that's shown. So as you can see, these top parts here, we've just got lines just coming off, but that doesn't mean it's just a line that has stopped. It is still continuing all the way around, but it's a bit difficult to draw a diagram going all the way around. So that's the reason why you just see lines coming off at the end, but it doesn't stop there. It is the full circle. So just keep that in mind. Okay, let's go back to here. It says here for this exam question, when two magnets are brought close to each other, they exert a force on each other. Okay, so describe how two bar magnets can be used to demonstrate a force of attraction and a force of repulsion. So remember, opposites attract, but you can't just say opposite. You have to be particular, like opposite what exactly. So you would say two opposite poles for the forces of attraction, and then two like poles. So like means exactly the same for forces of repulsion. You can be particular as well. You can say the forces of repulsion are positive and positive, or negative and negative, and then two opposite, you can say positive and negative, but just make sure you say them as explicit words in your answer. Don't just be really ambiguous with it. A lot of kids just say two opposite, but they don't refer to opposite what exactly. So just make sure you use the word poles. Okay, that's cool. What's the difference between a permanent magnet and an induced magnet? A permanent magnet always produces a magnetic field. So a fridge magnet, a bar magnet, magnetic compass, they've always got that field that I was attempting to draw before. They will always have it, so it's permanent. An induced magnet becomes magnetized when another magnetic field basically is around it. So for example, an iron nail is not magnetic by itself, but as soon as you put it onto a permanent magnet, it then becomes an induced magnet because you've put it inside a magnetic field. Okay, that's permanent and induced magnets. Okay, figure 3 here shows we've got a gymnast swings from one bar to the other bar several times. So just looking at the diagram, we can see the bar's higher in the first one and it's lower in the second one. So that's higher, this is lower. And then we've got weight acting upon it going downwards on the person. And then we've got a crash mat as well. So the gymnast swings from one bar to the other bar several times. Describe how the gravitational potential energy store and the kinetic energy store of the gymnast changes as she moves between the bars. So for 4 marks. So the first thing that you need to notice is she's going from a higher bar to a lower bar. So her height is decreasing. So we can say, so as the first mark, as height changes, we could talk about the gravitational potential energy store here. So even though energy stores really are paper 1, you can have a look at the paper 1 version of the equation sheet. Height affects gravitational potential energy. So as height changes, the gravitational potential energy store changes. That's your first mark. Your second mark comes from explaining, well, how does this exactly affect gravitational potential energy? You would say the gravitational potential energy decreases when moving to the lower bar. Again, that's because the height has decreased. Okay, so there you get 2 marks. You then can talk about the speed. So because the speed before, she's still on the second bar, but then she's moved to the second bar. So you would say her kinetic energy is increased because there's movement involved. So your third mark comes from saying as speed changes, kinetic energy changes because essentially there's movement involved. And so explaining that, so as speed changes, kinetic energy changes. You then need to explain, could you say anything about the center of mass? The center of mass is not changing because the center of mass is on the person. And that, well, it is changing because obviously she's moved from the next bar, but it's not really, your center of mass doesn't really affect gravitational potential energy store and kinetic energy store. So you wouldn't get the mark for that. Okay, so then your fourth mark comes from saying, I will just write it down, then I'll explain it. So transfer from gravitational potential energy to kinetic energy. Okay, so remember how, is this lesson being recorded? Yeah, you can, it's being recorded, so you can watch it later as well at a slow pace if you want. So transfer from gravitational potential energy to kinetic energy as height changes. So what we're talking about here is conservation of energy. So energy before all equals energy after. So she has to have got the kinetic energy from somewhere. So because the gravitational potential energy is decreasing and the kinetic energy is increasing, you've still kept that constant energy. So that's what this is referring to. So you can say, in other words as well, sum of kinetic energy and gravitational potential energy is constant. Also, please write the full words when you're doing your exam tomorrow. So write fully kinetic energy, write fully gravitational potential energy. So I've kept it simply here. So yeah, you could say either one. You could say that purple part, or you could say the blue part for that final mark. You'd get the mark either way. Okay, so that's for 4 marks. Even though it is really paper 1 knowledge, they can bring it over to paper 2 as well. So falling on a crash mat reduces the average deceleration of the gymnast compared to falling on a hard surface. So remember, deceleration, she's basically slowing down. Explain why reducing the deceleration is important to the gymnast. Well, imagine if she didn't have the crash mat there, what would happen? She would hit at a harder force, so injuring herself. But if she's got the crash mat, she's decelerating, she won't hit as hard. So the first mark comes from explaining that. So you would reduce the force exerted because she's going onto a crash mat, and then just explain, well, why is that good for the gymnast for your second mark? So you would say the risk of injury to the gymnast is reduced. You can answer your science paper in bullet points if you wish. It just prevents you from waffling because, say for example, this is a particular 2-mark question. If you end up writing 3 points, but then one of your points wrong, then you lose a mark. So just try and not waffle in the science papers. Just be really particular with your points. Okay, moving on. Okay, so a table tennis ball should be used if a ball bounces to at least 75% of the height it was dropped. Okay, so at least 75% of the height from the ball drop. A manufacturer tested a table tennis ball, and here's the result. So we can see from table 1, we've got the height the ball was dropped and the height of the bounce. So remember, they've said at least 75% of the height it's dropped from should be the bounce for it to be a good tennis ball. Determine whether the ball can be used. So even though this necessarily it's a calculation question, but it's not using any equations on your calculation sheet. It's just basic GCSE maths, which they do throw a lot of in paper 2. So it could be like percentage change, it could be working out percentage. They could test you on that. So just make sure you've not forgotten your GCSE maths for this. So for this, we need to check, is this height of bounce 75% of the height the ball was dropped from. So the way we could do that is we could say do 25.1, which is the bounce, divided by the height the ball was dropped from, and then we could times it by 100 to change it to a percentage. That gives you 83.7% to 1 decimal place. And the question said that the tennis ball will be used if it's at least 75%, so meaning 75% or more. So you would just say 83.7% is more than 75%. So therefore, yes, the ball can be used. So yeah, with a lot of calculation questions, it's not necessarily using the equations that you've been given. Sometimes it's just basic GCSE maths. Do you not do it the other way around because it says the height at which the ball was dropped? So the ball was dropped from 30 centimeters and the bounce that it came back up was 25.1. So another way you could do it is you could work out 75% of 30 and check is 25.1 within that range as well. So you wouldn't do 30 divided by 25.1. You'd get more than 100% there. That doesn't really make sense. You want to see is 25.1 75% of coming up back up to that 30. So yeah, a bit of basic maths. I guess if you did end up doing it the other way around, 30 divided by 25.1, you would have ended up getting an answer of more than 100%, which doesn't make sense. 25.1 is less than 100% of where the ball was dropped from. Okay, let's continue. So figure 5 shows 2 table tennis balls. The balls are different sizes but have the same mass. Okay, so different sizes, same mass. It says both balls were dropped onto the table from the same height. After they were dropped, the resultant force on the smaller ball was greater than the resultant force on the larger ball. Explain why. Well, the masses are the same. For combined science, what are the 6 mark methods? Are you referring to the practicals, Zainab? So it says here, after they were dropped, the resultant force on the smaller ball was greater than the resultant force on the larger ball. Explain why. The masses are the same, so that's not affecting it. And they were dropped from the same height, so that's also not affecting it. So your answer must come from this different sizes thing. They've kind of given you the answer in the question. So that's what you need to refer to first. You're going to say the smaller ball has a smaller surface area. So remember, that's just area around the whole ball. It's smaller compared to the bigger one. Yep, you're right. So we're going to speak about air resistance. So we're just going to say, so air resistance is less on the smaller ball. Because remember, what is resultant force? Resultant force is the overall force. So there's a force acting downwards on both of these because they've got the same mass. So that's not going to be affected. The one that's going to be affected is air resistance. Air resistance is going to be less on the smaller ball, but it's going to be more on the bigger ball. So yeah, air resistance is right. Okay, moving on. So we've got stopping distances. Stopping distances is the time it takes to stop your car, essentially. So there's 2 things that come into stopping a car. It's the time you take to think, which is your thinking distance, i.e. reaction time. How long does it take to think to actually press the brakes? This usually is between 0.2 seconds and 0.8 seconds. So just roughly remember that number. It takes less than a second for you to react to, say, somebody runs into the road. It would take you that quick to press the brake. And then braking distance is you actually pressing the brake. So a combination of thinking distance and braking distance contributes to your stopping distances. So if you increase any of thinking distance and braking distance, you increase your stopping distance. Yep, so you're right, condition of brakes and weather conditions. Just be careful which one you say your conditions are for. So for example, thinking distance is affected by like how fast you're going, distractions, if you've taken alcohol, drugs, tiredness, caffeine, that's all thinking. Braking distance can be affected by the conditions of the brakes, the tires, the roads, weather, whether it's icy, rainy, so on. When you do, you guys end up learning, when you learn to drive and you do your theory test, they do assess you on this for your theory test as well. So it will come back, you will see this again. So it says here, driver applies the brakes and the car comes to a stop. The force exerted by the brakes affects the braking distance. Give 2 other factors that affect the braking distance. Now, a lot of people get confused and they start writing stuff to do with the thinking distance. They're not talking about thinking distance, they're talking about braking distance. So stuff you could write here is like material of road surface. You could say stuff like the speed of the car, because the faster you're going in a car, the harder it is to stop. That's the reason why near schools you've got a lower speed limit, so 20 miles per hour, because you can stop a lot faster if your speed is low compared to if you were going faster. You could say wet or icy roads. You could say the gradient of the road. So like if you're on a hill or if you're going downwards, if you're going down a hill, it's a lot harder to press the brakes because you're going a lot faster down as well. So you could say that. And you could say mass of the car. A heavier car is harder to stop than a lighter car. So a truck would be harder to come to a stop compared to a small car. So just choose two of these for that question. Okay, we've got the electromagnetic spectrum now. You need to memorize the order. So you've got radio waves, microwaves, infrared, visible light, everything prior to visible light. So everything to the left of this is the least dangerous ones. So we use them for communications, night vision, so on. Everything after that are the more dangerous ones. Ultraviolet comes from the sun. X-rays we're using to find broken bones and such, but obviously it's quite dangerous to take a lot in. And then gamma rays, which we use for medical equipment sterilization. It causes cancer, but we also use it to cure cancer as well. So it's a bit of a strange one. Now, the important thing you need to remember for these are the wavelength and the frequencies. Let's start off with the frequency. So as you can see, with the gamma rays, so going across, they're higher frequencies. Now, what is frequency? Frequency is how many waves there are in 1 second. If you do forget this, you can figure it out from your equation sheet, because frequency equals 1 over the time period. So it's amount of waves per second, basically. So with the gamma, they're quite tight together. It's really high frequency. There's more waves per second compared to radio waves, which are quite far apart from each other. So it's a lower frequency. And that's the pattern across the electromagnetic spectrum. Okay, what about wavelength? What does wavelength mean? Wavelength, we spoke about it before. It's the length of one full wave. And as you can see, one full wave on radio waves is a lot longer compared to the gamma on the other side. So that's the reason why it's longer wavelength on the left-hand side and it goes to the shorter wavelengths. So just remember the opposite of each other. Please make sure you memorize some uses of all of these. I've wrote them here on the table so you can go over them at your own time. They could ask you about any of these, to be fair. Okay, so you don't want to be losing marks there. Okay, cool. Let's do this question. In a vacuum, so vacuum just is something like space, essentially. There's nothing in the air that's affecting waves, essentially. So in a vacuum, all electromagnetic waves travel at the same velocity. I think you would get the marks for saying speed, but velocity is the term that they use for speed in physics paper 2, mainly just because it's a vector quantity. Gamma waves have the greatest, well, we know they have the greatest frequency, as we've just spoken above. And radio waves have the greatest wavelength. Okay. Explain why it is important that the Earth's atmosphere absorbs gamma rays emitted by the sun. Well, gamma rays, they essentially cause cancers. So that's why it's really important that they absorb them. So for 2 marks, you would say, so people are not exposed to gamma radiation. And your second mark comes from explaining why is that bad. So your second mark's saying because gamma radiation can damage human tissue, which essentially causes cancer. So you can just say that as well. Make sure when you're speaking about ultraviolet, you speak about the particular cancer of skin cancer. Don't just say cancer generically. Ultraviolet hits the skin and essentially can cause skin cancers. Okay, let's continue. Okay, distance time graphs and velocity time graphs. Make sure you know the difference between each of them, sorry. So in a distance time graph, the gradient is speed, because if you have a look at your equation sheet, you should be aware of distance, speed, and time. So you can see speed is distance divided by time. So distance divided by time, y-axis divided by the x-axis, gradient is speed. One thing I want you to know as well, you guys probably used to using the DST triangle, but this is different on the equation sheet, so don't get thrown off by it. On the equation sheet that they will give you tomorrow, I'm going to highlight it in red because this puts people off. You can see it says S equals VT, where S, all over physics, S is referred to as distance, so in meters. So S in this case is not speed on the equation sheet, so don't get confused by that. If you want to use the original one that you used to, you can, but just be careful that you don't confuse S as speed. On here, you'll see this appear in quite a few places, so you can see there as well, S is not speed, it's distance or displacement, essentially. Is there anywhere else? Yeah, even here as well, S is not speed, S is distance. So that's why it's a lot better to use the worded versions of the equations and not the symbols, just in case you get confused. Okay, that's cool. Let's go back to the question. Okay, so make sure you know how to explain these as well. So as you can see, when the graph's going up, it's got a positive gradient, so it's increasing in speed, it's traveling a distance in a given time. If you've got a flat area on this graph, it's stopped because the distance it's traveling is not changing, it's staying on the same distance and time's going on, so the car's stopped and then it increases again. Now with the velocity time graph, velocity is essentially speed, but the vector version. So the gradient here, so gradient is velocity divided by time. And you should recognize that velocity divided by time from the above equations up here. So if I find velocity divided by time, it's right over here. And that's acceleration. So if you forget that the gradient of a velocity time graph is acceleration, you've got it on your equation sheet, so use it to your advantage. So change in velocity. Actually, one more thing to mention there as well. Remember that delta, the triangle sign, means change. So the way you work that out, you might be used to seeing it as acceleration equals v minus u divided by t. And if you forget that, you can see that. Do they give you it anywhere here? Yeah, over here. V minus u, in case you forget, it's the final velocity minus the initial velocity. So just keep that in mind. To work out the change in velocity is v minus u. So yeah, velocity divided by time is acceleration. So for that distance time graph, the gradient is acceleration, because y-axis divided by the x-axis is acceleration, and the area under the graph is the distance that's traveled. So they could make you work that out. To work out the area, you can split this into two triangles and a rectangle, work out all the areas of three separate shapes and add them together. Okay, so they're nice questions if they do come up tomorrow. So this question here, we've got a velocity time graph. So I've got time on the x-axis, I've got velocity on the y-axis. I know the gradient is the acceleration. I know area under the graph is the distance. It says here, here's an interesting question, determine the total time for which the velocity of the runner was increasing. So we can see the velocity of the runner increasing is in this section here and this section here, because in the other places it's just staying constant, as in, let me just draw it on here. It's constant in these two places and it's going downwards, it's decelerating in that section. So we need to work out the times for these two purple sections. So looking at this first part here, if I read downwards, how do I figure out what that is? This point is here. Well, I've got between 0 and 5, and there's 10 boxes. So if I do 5 minus 0 divided by 10, 5 divided by 10, which is a half. So each box is 0.5. So that's how you figure out how much one box is worth. Each box is 0.5, so that's 1. Let's do it in a different color. That's 1, 2, 3, and then that's 4. Okay, so we've got 4 minus 0 where it starts. That's just 4 for this one. Now we need to figure out the starting and ending of this one here. So if I look downwards, that's 10. And this one here, well, it's 5, 6, 7. So we're doing 10 minus 7, which is 3. And then we're just doing 4 seconds, add 3 seconds, which is 7 seconds. So you don't want to be losing basic marks on these kind of questions. Let's continue. It says determine the deceleration of the runner. Well, deceleration is basically acceleration, but a negative acceleration because you're slowing down. So you should know that's a gradient. So you need to work out the gradient of this line here. So you could do the triangle method, or I can find 2 coordinates on this line, and I can do the change in y divided by the change in x. So just work out the gradient, essentially. Now I can choose this point here, and I can choose that point here because that's where it starts and ends at deceleration, but you can use any point on that line. It doesn't really matter. So this one here is 14, 2, because I've just read off 14 then, and that's 2. This point over here is 24, 0. So I'm doing the gradient, which is change in y divided by change in x. Let me just write my 2 coordinates here. 14, 2. Okay, so change in y, I'm going to do 2 minus 0 divided by 14 minus 24. That's 2 over 10, minus 10, sorry, which is minus 0.2. So that's my deceleration. I expected a negative answer because it's a negative gradient going downwards. Okay, let's move on. Table 3 shows some information about 4 types of Bluetooth. So we can see we've got power, we've got the range. So range is how far it goes, power is how much power it takes. So sometimes it can cross a lot of information from paper 1 over. So don't forget that. We have got the paper 1 video on YouTube as well if you want to refresh your memory. So that's on there as well. It says here mobile phones use type 2, so this one, Bluetooth to communicate with other devices. Just 2 reasons why. So because the 2 factors they've given me for type 2 is the power and the range. So this is what we're going to speak about. So let's speak about the power first. So looking at the power compared to the other ones, it's in the middle. It's not too high, like there's 100 power, and it's not too low. So you could say it's a lower power compared to like type 1. So you could say a lower power, which, why is that good for a mobile phone? It means a mobile phone won't drain its battery that much. So you would say, so battery will not drain quickly, because you don't want the battery on a phone to drain quickly just because of Bluetooth. Something like 100 milliwatts, that would not work for the phone. Okay, and then now let's talk about the range. Well, you can see the range, it's not as low as these ones are. So, and it's not super high. You don't really need it that super high for Bluetooth, because think about real life uses of Bluetooth. I'm not going to connect something to Bluetooth from my phone miles and miles away from me. I don't need it 100 meters away. I need it either to a speaker or to send something to someone, or to connect headphones, like the headphones are right now. Bluetooth, the laptop isn't too far away from me. So you would just say that it's a good range, so a high range, which is basically enough for most uses with the phone. So that's just analyzing the information that's given to us in the question. A lot of science is just reiterating what you've been given in the question and just explaining it. Okay, let's do this next one. So I've got a feeling this experiment might come up tomorrow, this practical, but I'll go over the other ones as well if we do get time, just briefly. But here it's the water tank experiment, essentially. So you can see here in the question, they'll always give you the apparatus to be used. So please make sure you refer to all of them in your question, especially if it's a 6-mark one. So you can see here there's a wooden bar supported by elastic bands. We've got a light source, we've got the ripple tank, we've got water, we've got a screen on the bottom, and then we've got something to measure the distance, essentially. So it says here, describe how equipment in figure 11 can be used to measure the wavelength, frequency, and speed of a water wave. As soon as you start seeing measurements of things, you should go to your equation sheet on top and find what equation has wavelength, frequency, and speed inside it. So let's go to the top. Wavelength, speed, and frequency is this one here. So that's the first thing I'm going to do. I'm going to write that equation down in the question, because then I just need to figure out, where is it? So wave speed equals the frequency times the wavelength. So I just need to figure out, how do I need to find two of these certain things to be able to then use the equation to find out the third? So you should do this with almost every practical you get given in your paper tomorrow. So I essentially need to find two quantities to find the third. So I'm just going to roughly do this, but obviously make sure you do it in good detail. So for example, the frequency, what is frequency? Is how many waves are occurring per second. So you're using some element of time. So what apparatus are you going to be using for time? It's going to be a stopwatch. Obviously, make sure you write sentences. You would count the number of waves. Passing at a certain point in a fixed time. So make sure you're specific about that, because you want control variables. Make sure you know for this exam you control independent and dependent. Dependent is what you're measuring, independent is what you're changing. Controlling is what you're keeping the same, so it doesn't affect the investigation. So here you would count the number of waves passing a point in a fixed time period. You would then divide the time by the number of waves, because you want to determine the time for one wave, which is basically the time period. So the time period, remember, is t in that equation. And then you can figure out the frequency using this. So this, what we're doing is finding the time period of the waves. You substitute into this equation and you'll find the frequency. So we found the frequency. How do we find the wavelength? So the wavelength, we could use a ruler. Remember, wavelength is in meters. So we're using a ruler. So notice how I'm telling you what I'm using in each of these to find out what it is. So I'm using a ruler and I'm finding the distance across multiple waves. Now, the reason why I'm using multiple waves, it's very difficult to measure just between one wave because it's passing through. So you could measure the distance of multiple waves, and then you could divide by the number of waves to find one wave. And then using these two that you found, frequency and wavelength, you times them together and you find the wave speed, but make sure you write that in a worded form. So yeah, that's that experiment. I've kind of summarized that there, but they're good 6 markers. You don't want to be losing marks on them. Okay, make sure you know the difference between transverse and longitudinal waves and what each of them are. So these two are your keywords here. I'm going to highlight them. And make sure you know examples of each of them as well. So transverse waves, the electromagnetic waves are the main example for these. And it's sound waves for longitudinal waves. Okay, make sure you know what rarefactions and compressions are in a longitudinal wave as well. So these are your compressions, so where it's tight together, and your rarefactions are the ones where it's open. Sometimes you might see it like this actually, and then tight together and then loose again. So it's a bit like a spring when you're bouncing it and it's going back and forth. It looks like that. Okay, so let's look at this question. A teacher put a plastic duck in the ripple tank as shown in figure 12. So the plastic duck moved up and down as the water wave passed. How does movement of the plastic duck in figure 12 demonstrate water waves are transverse? So we know water waves are transverse. What are transverse waves? It's where the direction of the oscillation is perpendicular to the direction of the energy transfer. And that's exactly what's happening here. We can see the direction of the oscillation is that way, and then the movement of the duck is perpendicular to that. Got a memory trick for it, because you know how in transverse waves the T is perpendicular line and the two L's all show parallel lines. That's actually a pretty good idea, yeah. So the T is perpendicular to each other. That's a good way to remember it. And then in longitudinal, you said two L's. Okay, so you could say there's an L here. If that was a little L, actually, them two are parallel to each other. Yes, that's a really good memory trick, actually. So yeah, that's a cool trick. So here we can say that the duck, make sure you're particular to the question. The duck moves perpendicular to the direction of the wave travel. Okay, that's cool. Dairy milk ice cream dependent, measure independent change. That's a clever one as well. It's good that you have these mnemonics as well. They do help. I remember for chemistry paper 2, for the methane, ethane, propane, butane, it was monkeys eat peanut butter. So as long as it helped, that's the main thing, right? Okay, so we've got scalars and vectors. Remember, scalars only have a magnitude, so basically a size, but don't say the word size, say the word magnitude, which I've wrote here. And vectors have magnitude and direction, so you're telling it which direction it's going in. And there's some examples there. So the speed is a scalar version. The vector version of speed is velocity. The scalar version of is distance, and the vector version of distance is displacement. So that's the reason why the colors are the same. Okay. We've got a question here. Some quantities are scalars and some are vectors. Which of the following quantities are scalars? That's distance and speed. You don't want to be losing basic marks on stuff like this. Give the difference between a vector quantity and a scalar quantity. Well, a scalar just has magnitude, and a vector has magnitude and direction. Please make sure you write the full words, scalar and vector. Just doing this just because of time. Okay, figure 9 shows a free body diagram. Remember, a free body diagram is just something that you put your free point in the middle, and then all the arrows are the forces acting upon that. Okay, so it's a free body diagram for an aeroplane flying at a constant speed and a constant height. So same speed, same height. The speed of the airplane is much greater than the speed of the airplane is much greater than the speed at which the airplane lands. Okay. Explain how forces need to change so that the airplane can land. So when an airplane's landing, think about it, you need to go down. Now, you can't change the weight of an airplane. You can't exactly chip away the mass when the airplane's at height. So we can't really change the weight. So because we can't change the weight and we need the plane to go down, we need the resultant force to be overall down. So we can decrease the lift. So we can say lift must decrease as weight can't change. So that's your first mark. So lift must decrease as weight can't change. So explain why that's a thing. Is this question higher foundation? This is both for higher and foundation. So there is a resultant force downwards because you've decreased the lift, so therefore the weight's more down, so it's going to go down. Okay, so we've spoke about that for 2 marks. Now let's speak about these two. Now, we can't change the air resistance because air resistance is something that's just acting upon the plane because the plane's there and it's going through the air. So we can change the thrust. So we can say thrust decreases. So there is a resultant force in the opposite direction. Okay. So this is the reason why it says the speed of the airplane is much greater than the speed at which the airplane lands. So the speed's decreasing. So that's the reason why your thrust decreases, because you want more air resistance, so your speed is slowing down. Okay, so that I've got that from the question. Okay, so 4 marks is kind of referred back to the question. It's talking about resultant forces. They can give you any example in the exam tomorrow. It's just using what they've given you in the question to figure out where you want your resultant force to be. Okay, just before I move on to the higher content, I just want to go over some things just before I go on to higher. So this is still for both foundation and higher. If they ask you which materials are magnetic, the examples usually are iron and steel. So stuff that's not magnetic is aluminium. Think about it. If you had aluminium foil in your cupboard, you can't stick it to your fridge. It's not. Yeah, I am going to go over Fleming's left-hand rule because that's just higher. So iron and steel are magnetic. Stuff like aluminium is not magnetic. You can't stick it to your fridge. Copper is not magnetic, and tin is not magnetic. I want to quickly go over Newton's laws of motion. So the first law, actually, rather than writing this down, just to save time, I'm going to get out the summary sheet. Okay. Okay, right here. Okay, so Newton's laws of motion. The first law is talking about the resultant force being 0. So if the resultant force is 0 and the object is stationary, so remember stationary means still, then the object will stay stationary. That's the first point. If the resultant force is 0, but your object is moving at constant speed, it will stay at constant speed because there's no resultant force. Okay, the second law is just the equation. Force equals mass times acceleration. You're given this. Another thing you can say about this, so the second law, force equals mass times acceleration. Now, when mass can't really change, if you've got mass of something, it's going to stay the same unless you chip away at it. So another way you might see this is force is directly proportional to acceleration. So because I've got a direct proportion relationship, remember direct proportional looks like that. They might tell you to identify the graph. If you increase acceleration, you're increasing force is what that relationship means. And then the third law says when two objects interact, for every action, there's an equal and opposite reaction. So for example, if I'm pushing a wall, the reason why the wall's not falling over is because there's an equal and opposite force acting upon me. Okay. And finally, just want to speak about what a solenoid is. So a solenoid is if you've got an iron core, so just say an iron core in the middle, remember iron's magnetic, and you wrap the wire around that core. We call this a solenoid electromagnet. And the reason why this is better than just having a wire is because it's a stronger magnetic field. So you know the way the magnetic fields looked like for the North and South Pole and for the Earth, like this. That's what it looks like on a solenoid as well. That's the reason why they're a lot more better to use, better, stronger, better magnetic field, more stronger. If I had just a wire, let's say the current's going this way up, there's just a magnetic field that just looks like this. It's just going around, and this is where you use the right hand rule. So you get your right hand. If you curve it in, your thumb represents the current. So in this case, the current's going upwards. So my magnetic field is the direction my fingers are going in, which is in this direction, this way. Now, the question might ask, how can I change the magnetic field to go the other way around? All I have to do is I have to change the current. So if current's going downwards, now my magnetic field is flipped the other way around. Okay, so that's the end for both foundation and higher. I'm going to go over to the higher content now. So if you are doing foundation and you want to drop off, you can. good luck with the exam tomorrow, but let's cover the higher stuff now. Okay, so for higher, you need to know about momentum. So momentum is basically motion. It's a scientific word for motion. So the equation, they give it to you, it's mass times velocity. So something that's heavier will have more momentum, so a higher mass, more momentum. And if it's got a higher speed, i.e. velocity, then it's got more momentum as well. So you get given that. Let's have a look at this question. So we've got bumper cars here, momentum. Give two factors that affect the momentum of each bumper car. Well, you're given the equation on your equation sheet, use it. Mass affects momentum and velocity affects momentum. There's other stuff you can say as well, like friction, for example, but I wouldn't recommend writing that. They want you to just state the two things that the equation tells you. So mass and velocity affects momentum. Okay, next question. The bumper cars crash into each other and stop. Explain why both bumper cars stop after the crash. So this is about conservation of momentum. So if I just go back up here, conservation of momentum says anytime you see the word conservation, whatever's before is the same after. So same with conservation of energy. Energy can't be created or destroyed. Whatever's before is always after. Same with conservation of mass. Whatever mass you put into a reaction, it's after as well. So same with conservation of momentum. In a closed system, momentum before equals momentum after. So, as we can see, with this question, the bumper cars crash into each other and stop. So if they've stopped after, that means momentum after is zero because they've stopped. There's no velocity, and momentum equals mass times velocity. If velocity is zero, momentum is zero. So that's what I'm going to talk about for the first mark. So total momentum after equals zero. So after the collision, essentially. Because the cars are stationary, they've stopped. So you could write that down as well. So therefore, because of conservation of momentum, the momentum before equals the momentum after. So the momentum before must also be zero. So you would say the momentum of each.
Akib, can you shut up, bro?
The momentum of each car before the collision was equal in magnitude. Okay, I'll write this down and then I'll explain it. So the momentum of each car before the collision was equal in magnitude. Reason why is because of conservation of momentum. So you would write that down. Because of conservation of momentum, you would say the total momentum of the cars was zero before the collision. So there's just a conservation of momentum question. We know it stopped after, so because it stopped, the velocity is zero, so therefore momentum is zero, as we discussed. So therefore it must be zero before, and then you explain that with conservation of momentum, why both bumper cars came to a stop when they crashed. So these are the three examples they could ask you about, so rebound, coupling, or recoil as well. So I guess this recoil example was what this bumper cars one was as well. So when you're shooting something out of a cannon, because the ball's not being shot out of the cannon, the momentum is zero because there's no velocity. So therefore, after it must also equal zero as well. Even though there is movement, they will cancel out and it will be zero as well because momentum before equals the momentum after. Okay, so moving on. Fleming's left-hand rule now. So your left hand, you've got your thumb, index finger, and your second finger. Your thumb represents motion, so where the actual motion will be going. This is what they usually ask you about in the exam. Your first finger is a magnetic field. Remember, it goes from north to south. Your magnetic field is north to south. And then your second finger is your current. So the middle finger basically is your current. So looking at this question, it shows a wire in a magnetic field. The direction of the current is shown. So current's going that way. So my second finger is going towards. I know it's going from north to south, the magnetic field. So I'll draw that in. It's going north to south. North to south. It says there's a force on the wire due to the current in the magnetic field. Which direction is the force? So we're basically working out the motion. So let's, it's a bit fiddly, but the current, which is the second finger, is going basically towards. My magnetic field is going north to south, so I'm going to have to flip it downwards like that. So there's my magnetic field going north to south. This might be in the opposite direction for you. The current's going towards the paper, so motion's going downwards. My thumb's pointing down. So have a try at that yourself as well. See if it does work. So that's why it is. It says give two ways that the direction of the force on the wire could be reversed. It's just the magnetic field and the current. So you would just need to reverse them two for it to work. So you would say that you could reverse the direction of the current. So the current, or it's the magnetic field. So you could reverse the direction of the magnetic field. So it's basically the other two fingers, what they were representing. So just make sure you remember what each finger represents in Fleming's left-hand rule. And I guess in the exam tomorrow, if you start seeing everyone do the fingers, then you know the questions come up as well. So that might be a little bit of a clue as well. Just put the mark scheme for this question here. So we've got a simple motor. Explain why the coil rotates when there's a current in the coil. So the reason why the coil rotates, so these are your points near, right? So you speak about there's a magnetic field due to the permanent magnet. It goes from north to south. As soon as you see that north and south, you know there's a magnetic field. And current in a wire causes a magnetic field. So remember, it's like you've got a magnetic field from north to south, but then you've got a magnetic field from the wire. So you put a magnetic field into another magnetic field, which is going to basically cause it to move. So explaining that current is in opposite directions in each side of the coil. So we spoke about the current. Forces act in an opposite direction of each other. So therefore, the coil rotates, basically is what that last part says. So yeah, just make sure you memorize the mark scheme for that. It tends to be the same almost every single year. So I've put that in. Okay, we've got the wavefront diagram. So wavefront diagrams are used to explain why light refracts when it passes from air into glass. So remember, refract just basically means bend. So we've gone from air to glass over here, and we can see it's bent from using the wavefront diagram. The 3 marks, it says explain why light refracts as it passes from air into glass. Well, what's the difference between air and glass? You can say glass is denser than air. So you would say, so the edge of the wave entering glass slows down. So there's basically a change in velocity. So it slows down the wave coming in to the glass, but part of the wave in the air, that's basically still going faster, so continues at a higher velocity, or you could say speed. So causing a change in direction. So I'll just explain that again once more. So glass is denser than air. So because glass is denser, the speed of the wave is going to change. So the speed is higher in the air and it's lower in the glass. So because there's 2 differences in speed, that's what's causing the bend. So that's the last part of that covered. So I've covered as much as I possibly can. If you've got any questions, do ask. I'll get this uploaded. I'll get the notes sent out. And that's the last session for this year. So I hope you found all the other sessions useful. I hope tomorrow's exam goes well, and I hope you found use as well in all these sessions that we've prepared. Yeah, good luck on the exam tomorrow, guys, and hopefully it all goes well on results day as well, and you have a much needed break after. No worries. But yeah, good luck with tomorrow, guys, and hopefully see you, probably not see you on another one, but we'll hear from you definitely on results day. No worries. Okay, bye, guys.